Welcome to our discussion. I'm Norman Peckham, and I have with me Dr. Ariel Roth. This is going to be the second of a two-part series on the origin, function, and evolution of eyes. What a fascinating time we had with simple and complex eyes last time. What are you going to show us today?
Well, I want to start out with a statement, the same statement I started out in the last talk, which dealt with Darwin's Origin of Species and his famous book. There he talks about some of the details you find in some of these eyes, and we want to look at one of these. But again, what he says there, to suppose that the eye, with all its inimitable contrivances for adjusting the focus to different distances, for admitting different amounts of light, and for the correction of spherical and chromatic aberration, could have been formed by natural selection, seems, I freely confess, absurd in the highest degree. Now, he's talking there about certain of the problems of eyes done in correcting, including spherical aberration. We want to talk a little bit about spherical aberration. Most people are not that familiar with spherical aberration, but let me give you an example of an organism that corrects for spherical aberration, and it's a trilobite. If you go up to high mountains in Western Canada, there'll be Mount Stevens there, and here's a picture of it. And you see the dark layer there, and kind of in the middle of it.
Yes.
You find all kinds of trilobites there, beautifully preserved trilobites in there. Now, this is way up in the mountains, but this is way down in the geologic column. This is the region of the Cambrian explosion. This is where we first find an abundance of animals, all kinds of various kinds of animals there at this, and among these are trilobites. And this is a picture of a trilobite there from Mount Stevens.
Looks a lot like a horseshoe crab from here.
Yeah, well, they're somewhat more remotely related.
Yeah, well, they're both bottom of the sea creatures.
And you can see the red arrow there. It points to an eye and a trilobite. Now, there are some trilobites that have extremely sophisticated kind of eyes, and these eyes correct for spherical aberration, this problem that Darwin was concerned about. The eye of a trilobite is not like ours. It's not a simple camera type of eye. It's a compound eye. It's like the eye of an insect or of a dragonfly, you know, those great big eyes that a dragonfly has and so on, where they have many different tubes, each one pointing in a slightly different direction, and they put the picture obtained from those various tubes. But each one of those tubes has to be precisely focused, or it will see the same thing as the tube next to it. And as I mentioned, there are 28,000 tubes in the eye of a dragonfly. And you see the green lens there and so on. That's just part of the complex. The eye of the trilobite has complex optics. There's more to it than just one superficial lens there. But that superficial lens has a shape that corrects for this spherical aberration. Well, what is spherical aberration? Here's a diagram showing you what is involved here. We have a white lens right here, and various light rays coming in. And an ordinary shaped lens with a curved surface. The light coming in from parallel rays or from distance and so on will not focus or converge in the same place, because different parts of the lens bend it in different ways. And you can notice here these outer rays converge in front of this particular line, those in the middle over here, and so on. This is the problem of spherical aberration, and if you have too much of it, you're not going to see a good picture, which is, of course, what we want, a sharp image, to be able to see the details. Well, there were two outstanding pioneer scientists philosophers and so on. The name of Descartes, most people have heard of him, famous mathematician, philosopher, Huygens, who devised a solution to this question of spherical aberration. If you shape your lens the way this lens is shaped, the white shape you see there, the parallel rays that come in from a distance into the eye will all focus on one point, as is shown by the red arrow. And so there are ways of correcting for this. Our eyes, we correct for it certainly by reducing the aperture and so on in our lenses. But the trilobite does it in a different way. They have this kind of a lens.
So they have this
odd-shaped
lens that corrects for spherical aberration.
Yes.
Down here in the bottom of the Precambrian layer.
The very first significant eyes we find in the fossil record have this here, and we have no record of organisms evolving this kind of a lens before this. You expect all kinds of changes for trial and errors, mutation after mutation, so on, to try and do this. Furthermore, this lens in the trilobite is made out of the mineral calcite. Calcite is a complex crystal, and it has 3 indices of refraction. By this we mean it bends light at different angles in 3 different strengths, depending on which face of the crystal you happen to be sending the light through. And this would confuse the picture tremendously, because you have to have the right index of refraction in order to get the right correction for spherical aberration. And they found out that the lenses in these trilobites made of this calcite all had the crystals oriented in the same direction to give the right correction for spherical aberration.
That doesn't sound very random.
It doesn't sound very random. It's one of those marvelous things you find, and one of those things that suggests, well, maybe God created this. Yeah. Let's look at another interesting issue, and that is the inverted retina. The eye of squid and octopus have what they call a verted or non-inverted type of retina. They have what is considered the right retina, the verted retina. And you have here the eye of a cephalopod, and the lens, the blue lens there, and the retina to the left there, and so on. And the light-sensitive part of the cells in that retina face that lens directly. They face that lens directly. The light comes from the lens and goes directly to the light-sensitive part. And so that's considered to be the best part, the verted retina. Now, when you get to a typical vertebrate like you and I, we have an inverted retina, what is considered inverted retina. And this is really puzzling at first, but extremely interesting when you know the details. And here the light comes in through that blue lens and it goes over to the retina and so on. But before it gets to the light-sensitive part, it has to go through layers of nerve cells and the nucleus and so on of the light-sensitive cells, and then finally it gets to the light-sensitive part. This diagram will illustrate to you a little bit what we're talking about here. The verted retina, or the eye, of a squid, for instance, is described in the upper picture, part of the picture. The inverted retina is described in the lower part, and that's the inverted is the kind of eye that we have, and that all vertebrates, snakes, alligators, and so on, birds, and you and I all have what is called an inverted retina. type of thing. The light's coming from right to left, and we've indicated in yellow there where it's trapped. Now, in the verted retina, the light is trapped by those tubes, those microvillas of a rhabdome, and so the light hits that first, almost first. There's some few pigment granules in front that sometimes migrate back and forth according to how much light there is. It's kind of a light control system that eye has, but the yellow part is where it's trapped. And that's the verted retina. Now, the lower part, we have the inverted retina. And there the light, again, coming from the right, going to the left, has to travel through all these data processing neurons and nerve fibers before it gets to the light sensitive part, which is the yellow part of those cells to the left there. People went, why build an eye like this where the light has to go through all this stuff before it reaches the light sensitive parts? Well, evolutionists feel this represents bad design. And let me quote you from a couple of these evolutionists. Jared Diamond, University of California, Los Angeles. He says, how are the vessels and nerves aren't located behind the photoreceptors where any sensible engineer would have placed them, but out in front of them where they screen some of the incoming light. A camera designer who committed such a blunder would be fired immediately. By contrast, the eyes of the lowly squid, with the nerves artfully hidden behind the photoreceptors, are an example of design perfection. If the Creator had indeed lavished his best design on the creature he shaped in his own image, creationists would surely have to conclude that God is really a squid. Trying to, of course, make fun of the idea of creation.
That assumes that a squid can see better. Do we have any evidence of that?
No, I suspect we see better. And I'll explain to you why in just a minute. William Thwaites, San Diego State University, he states, vertebrates are cursive and inside-out retina in the eye. Did God at the time of the fall turn the vertebrate retina inside out? Again, concerned about creationist beliefs. Richard Dawkins, Oxford University, says, any engineer would laugh at any suggestion that the photocells might point away from the light with their wires departing on the side nearest to the light. Each photocell is in effect wired backwards. Let's look at some of the details of this here. This is the inverted retina. Light comes from the right and goes towards the left. It has to go through all the nerve cells and fibers you see there to finally reach the light-sensitive cells you see at the left. And that light is trapped in the rods and cones where you see the red arrows. Rods are for dim light and cones are for colored light. One rod can have as many as 40 million capturing rhodopsin molecules, which trap the light. And that when light hits one of those molecules, the molecule is bent. And then you have it affecting other molecules, a few others will affect many more.
Kind of a cascading thing?
Cascade, an avalanche type of thing. Mm-hmm. And it finally changes the voltage on the outside of that cell, and the message is sent to the brain, hey, we saw something, type of thing. The inverted retina has a system that is constantly replacing those molecules that we were telling you about. Towards the left, you see the lines representing the discs in the yellow region behind the red arrows. Actually, there can be 1,000 discs in a single sensitive cell. The discs are constantly being produced and replaced, In the diagram, they travel towards the left, as indicated by the red arrows. They are absorbed in the whitish layer to the left, which is identified there as pigment epithelium. A disintegrating disc is designated in that layer at the end of the rod cells. And so we have a constant fresh supply of these pigment-bearing discs. Our eyes take no rest at all. This is going on. We replace about 80 to 90 discs per day. Frog, a little more slowly, 30 to 40 discs per day, but the frog still has an inverted retina, and still you have this process for providing what is considered necessary fresh supply of these cells that are, or these molecules, I should say, that are sensitive to light. What if we should turn this around, like the evolutionists say we should do? We would have these cells facing out here, and then we'd have the discs being poured out here.
Into the eye.
Into the eye, yes. And you'd be, producing maybe about 10 billion of these per day, these discs. I mean, this is not very good for seeing, you understand.
Plug up the eye.
Very fortunately, we have this pigment epithelium that's absorbing these cells. Furthermore, we got this choroid blood supply here that provides nutrients. These are some of the most active cells we have in our body, constantly replacing this pigment there. And but if you put the pigment epithelium out in front here, it has pigment. That would not be very good. If you put the choroid blood supply, which is so important to the pigment epithelium, again, you would not be able to see very well. I mean, blood is very debilitating to see. So it looks like we have a system here that's very good for light to be transmitted through a system that's constantly replacing the molecules that are sensitive to light. And it seems to work very well. In addition to that, it has been found that there are some cells that carry that light straight through there. So all this concern about light getting through has been solved by what we call Mueller cells that are in the retina. This is a beam of light coming in, and Mueller cells will carry that light through all those various nerves to the part, the light-sensitive rods and cones, light-sensitive part that receive. So we've got a mechanism for carrying the light through there anyway. All this concern about light getting through there does not seem to be supported by this recent discovery. It was made in 2007.
Got a light pipe straight to the retina.
Light pipe straight through that retina,
like that.
and so on. And and we have to do. You can't argue with this. The retina. It's a system that works. Let's just look a little bit more just at the complexity of the eye. This is a diagram of a eye, and I realize you can't see all the parts. I just wanted to point out something to you. This is an enlargement of the wall of the eye here, and this is an enlargement of the retina. Just a small part of the retina. The retina is this whole part right here. See, there are many parts. I just wanted to make the point that the eye is extremely complex. But the problem that has been raised by evolutionists about the inverted retina is probably not all that bad, because we have in the vertebrate eye, the eye we have and so on, we have a fovea, and you see it in the diagram there, right opposite that lens, at the left, fovea, and that. And there, the fibers and the nerve cells and so on are much thinner. The fibers radiate out from that region. That's where we see our acute vision, and that's what you're using to read the various words on this diagram, for instance, in your fovea. You have about 30,000 cones there, and they provide you with the acute vision that you use in reading, type of thing. There are many other things in the eye that are challenging in terms of how they could arise all by themselves. For instance, you know, your pupil gets smaller and larger. Which evolved first, the muscles that make it smaller or the muscles that make it larger? You have to have both. And you would not have survival value until both were there. Could both systems arise by random changes and so on? You don't have survival value until the system works, type of thing. You've got focusing, changing the shape of the lens. You can say the same thing about that. What changes the shape of that? Well, you got muscles that change the shape of the lens. Those muscles are not going to work unless you have a center in your brain that controls those muscles, and that center is going to be useless unless there's a system to tell that the picture is out of focus. What are the problems here? How could parts of those systems evolve when they have no survival value until the other parts are there so it can work? There's no point in evolving a control system for the lens unless you have something that tells you things are out of focus.
And so it wouldn't happen unless you had it there. Right.
So this is just a last little point I want to make here. This is an eye. They've removed parts of the skull and so on to show you the inside of the head, to show you the inside here. And you have here a superior oblique muscle, and you have a tendon right here, and you've got what is called a trochlea there. And that tendon goes through that trochlea as a pulley, so that when the superior oblique muscle pulls this way, it pulls the eye forward and up in that direction, because it's attached here to the eye that you see here. Well, which evolved first? The long tendon, which you'd have to have, the trochlea, through which the tendon goes, it slides through there back and forth, or the system that threads that tendon through the trochlea. And this is not going to work till you have all those three things working. Could random changes do this? You have no survival value till all those three things are there, type of thing. So it's another case of things are too complex. It doesn't seem they could have arisen by just natural selection and survival of physics, because survival of physics would tend to get rid of all these extra parts that don't work. Charles Darwin, again back in his Origins of Species, he says, if it could be demonstrated that any complex organ existed which could not possibly have been formed by numerous successive slight modifications, my theory would absolutely break down, but I can find no such case. He tries to protect himself. Notice his wording, you know, he says, could not possibly. In other words, he's using, you know, just prove that it's impossible type of argumentation. Well, you're kind of protected because you can imagine most things are possible and so on. But obviously, Charles Darwin did not consider the problem of interdependent parts when he talks of numerous slight modifications. And that's throughout his book. And this is these slow mutations, these very slight changes and steps and so on. Because we have all kinds of things that would, if you went through numerous small, slight changes that are non-functional until the whole system works. I mean, that trochlea I was showing you in the last slide is an example of that and so on. And we've got so many things like this in so many organisms. It very much looks, you know, when he says his theory would absolutely break down. His theory is absolutely broken down many times when you consider complexities like the eye, interdependent parts. The scientific data makes it difficult to think that there isn't a creator, and to me the conclusions are rather obvious. The eye was designed by God. It's just too complex and intricate.
Well, thank you so much. It seems once again that the complex eye of the lowly little trilobite, down way down with the primitive creatures in the in the Cambrian layer, shows big evidence that it didn't happen in a slow way, that so much happened too early. So we've got to leave it there. Our time is gone. But we'll be back next time when we continue our search for where is truth. If you would like additional free information about these discussions, there is a PowerPoint resource available on the internet that covers many more details than could be provided in this lecture series. The resource is titled The Bible and Science and is available at scienceandscriptures.com. Be sure to add an S at the end of the word Scriptures to get to the right web page. The Bible and Science resource follows the same sequence of topics as the Where is Truth series, but it is divided into 17 separate discussions instead of the 14 videos of the Where is Truth series. The title of the discussions, an introductory outline, and an index will lead you to the topics you want. The Bible and Science discussions served as the resource for the Where is Truth videos. To facilitate understanding and learning, each of the 17 PowerPoint discussions in the Bible and Science resource is provided with a set of questions and their answers. You will find these at the end of each PowerPoint presentation. The Bible and Science resource was designed especially for students and teachers. However, it can be of great help to anybody interested in the topics.